Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior researcher at the SETI Institute and also chief scientific officer at Unistellar. And today I'm going to be the host of this interesting SETI Live. They're always interesting, but this one I like it very much because we invited with us Natasha Hurley-Walker. How are you, Natasha?
Hi, Frank. Great to be here. Very
I'm
well, thank
good.
you. How are you?
So Natasha is a leading radio astronomer from Curtin University in Australia. She's the lead of research, which has been published quite recently in Nature about a very interesting signal called GPM J1839-10, a star like no other, I would say, an enigmatic cosmic entity that has been sending us messages every 20 minutes for almost 30 years. So that's the goal, that's the topic of this conversation. So I'm just gonna warn our users that there is a slight delay between Natasha and I. So we may try to we're gonna try to do what we used to do in the past. I'm making a sign when I want to interrupt Natasha, and Natasha will make a sign. So if you see us putting the hands up and down like this, it's not because we're playing a game. It's because we don't want to over talk about each other. Hi, Natasha. I'm glad to see you again. So um, tell us about this discovery. Tell us a bit about what is about.
Great. Well, yeah, it's lovely to be here, and I'm so excited about this discovery. So I actually spoke with your wonderful audience last year about a very similar discovery where we discovered a radio source that was repeating every 18 minutes in space. But that source was only active for a couple of months. And so that made it very difficult to understand what it was. So this new source, JPM J1839, we discovered it using a bespoke campaign where we scanned the skies with the Murchison Wide Field Array, which is a radio telescope here in Australia, searching specifically for this kind of radio source. We figured if we'd seen one, there must be more out there. And we were really lucky. Pretty much as soon as we switched the telescope on and we started scanning and we used our new detection algorithms, we picked up a new signal, which was fantastic, right? Very exciting. The key thing that we can do when we've found something and we're detecting it in real time is that we can start following it up with new telescopes, with other wavelengths, and try and get at the heart of it. But very quickly we found, right, this source repeats every 22 minutes, so a little bit slower than the previous source. And sometimes the pulses are on for as long as 5 minutes. So you can imagine like this blast of cosmic static coming out at you, and then it switches off completely for 17 minutes, and then it comes back on again for 5 minutes. Very strange behavior and very difficult to explain. What was even weirder was when we started looking back through our archives, going through data from the Giant Meter Wave Radio Telescope, which is in India, and the Very Large Array, which of course is the telescope that Jodie Foster is listening to in Contact, that has one of the largest digital archives of radio astronomy information in the world. And we went back through that data and we found that the source has been on this entire time. It's been sitting there in the data waiting to be found for 30 years. Our first detection was in 1988. So I was just 5 years old. So this is a really enigmatic source. It's been on all this time, which completely defies our expectations. And yeah, it's an exciting discovery, which is why it's gone into Nature.
Thank you. Thank you for this good summary. So before we continue digging into this interesting signal, I want to say that we have people joining us from Texas, from California, from Mexico City, from New York, Accord, New York, more Mexico City, from Canada, Florida, Atlanta, Green Bank, not far away from Green Bank, Fort Lauderdale in Tasmania, and many places. Santa Rosa, France, Ohio, Australia, such a big continent. You should say which city you're watching us from, and so on. So yeah, welcome. We are talking with Natasha Hurley-Walker about this enigmatic signal, periodic signal that's been detected and using the MeerKAT radio antenna, and seems to have been active periodically, not continuously, for 30 years. So in the big scheme of all these weird radio signals, you already talked about one in our SETI talks in the past. Why this one is so weird? What exactly these properties that you think is make it bizarre?
Right. Well, of course, as you say, we know lots of repeating radio signals already. There are pulsars, right, which were discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. And those are thought to be neutron stars that produce radio waves that come out of their poles. And as they rotate around, the radio waves intersect our line of sight, a bit like a lighthouse beam sweeping across our eyes. And so the rotation rate of the neutron star ends up giving us the periodic flashes of radio light, right? So that's a well-known phenomenon, and we've understood that, or we thought we understood that, for like the last 50 years. The key there is that neutron stars are extremely magnetic. So we're talking the strongest magnetic fields in the universe, and they're rotating incredibly rapidly, right? Every second, a mass that is bigger than our sun, crammed into the size of a few tens of kilometers, rotates around, and like every second or even every few milliseconds. Absolutely phenomenal energies and phenomenal speeds. It's that torque, it's that change of magnetic field across space that we think generates the radio emission. Now, our sources are also periodically repeating, indeed, incredibly precisely. Our source that we've timed to 22 minutes hasn't varied in its period over the 33 years that we've measured it. It is just like a cosmic flywheel, very similar to a pulsar. The problem is that the physics of how we generate that radio emission really breaks down at these slow rotation speeds. So it's just kind of gently turning around like this. There's not enough energy there to produce the radio waves, at least according to our theories. So there's this concept of the death valley, which is as pulsars slow down in space, they're losing energy all the time, their radio emission eventually ceases. And up to this point, we had never seen any pulsars beyond the death valley, or below the death line, as it's called, until now. So our source, we've timed it very precisely. It's below the death line. It should not be producing radio emission, which of course begs the question, why is it doing this? How is it doing this? And how has it been doing it for 33 years?
So what's your interpretation? What in this paper, you have multiple ideas of what this source could be. Can you give us a bit some hints of ideas about, I heard about magnetars and things like that. So maybe you can elaborate a bit more.
I'd love to. So with the first source, it was only on for a few months. And so you could kind of say, all right, perhaps it's a neutron star with a very complex magnetic field called a magnetar. And as that magnetic field changes and twists and decays, it can kind of briefly rearrange itself, and that can give us enough energy to produce the radio emission. That's fine. There are lots of normal, as much as a highly magnetic ball of neutrons rotating hundreds of light years away is normal. There's plenty of canonical magnetars, which behave just like this, right? They have rotation speeds of, they rotate once every few seconds. They have twisted magnetic fields. We can see them in X-rays. So that's how we know that there's these really strong magnetic fields. They're like distorting the crust. And every so often they go into outbursts. They produce radio waves for a few months. So that seemed like a really good fit to our first detection, which was only on for a few months. The problem is the new source has been on for 33 years, and the X-ray magnetars are not supposed to be able to sustain radio emission that long. Also, we've done very sensitive observations with the XMM Newton X-ray telescope at the same time as the Australia Square Kilometre Array Pathfinder telescope. So we've looked in X-ray and radio at the same time. Normal magnetars should produce both X-ray and radio at the same time, or maybe with a slight delay, whereas we see absolutely no X-rays at all from this source. So that makes the magnetar interpretation really challenging, and we don't really have a good answer for that. Maybe we find a new kind of magnetar. There's also the potential that it is a white dwarf. So neutron stars are one way that quite massive stars kind of end up at the end of their lives. Any more massive than that, and they end up as black holes. Less massive stars, like our own sun, end up as white dwarfs. So that's not quite as massive, so it doesn't compress all the mass into neutrons. Instead, you end up with this strange state of matter called degenerate matter, which is still atoms, but they're just really squashed together. So you have like a ball about the size of the Earth, made of atoms densely packed, and they have pretty strong magnetic fields, a few thousand times less strong than neutron stars, but they're still kind of strong. And it's thought that sometimes these could also be pulsars. 20 minutes is a reasonable rotation rate for a white dwarf. The problem is when you actually do all the math, it doesn't quite work. You still don't have enough kind of torque across space to rip it apart to produce the radio emission. So it's a working theory that maybe it's some kind of white dwarf that we don't understand yet. But it's just a theory. We need to do more observations in order to really find out.
Yeah, that's gonna bring me to my next question. But before, I want to say hi to people joining us from Colorado, from Peru, from Kosovo, from Texas. More people from Texas. Welcome.
Oh, great.
We are talking about a strange signal. Where did you grow up? Which city?
Texas, Houston.
All right. Okay. Okay. So we have this weird signal detected by radio, periodic, active for 30 years. We don't have a clear explanation of what it could be. You have some hints, Magneta, white dwarf, maybe something completely exotic that we don't really understand or we have not yet discovered, right? The universe is huge, but the galaxy has 100 billion stars and probably thousands or millions of magnetas of different kind of species of stars. So what is the next steps in your research to nail down the true nature of this weird signal?
There's a few different techniques. So one of the things that one of my co-authors, Nanda Ria, who works in Spain, has been working on is like evolutionary modeling. So creating simulations of populations of white dwarfs and neutron stars and seeing how they evolve and whether there's any kind of reasonable physics that can produce the radio transients that we're seeing. Another angle, which I'm more of an observer and less of a theorist, is of course to find more. And so I'm looking at a range of different radio telescopes across the world and working out how best we could search the data, both in surveys that we're taking at the moment, and of course the vast, rich archives, which we now know must contain hundreds of these objects. And if we can find more of them and we can understand where they are in our galaxy, then that's going to make some explanations more or less likely. For instance, we know that magnetas should tend to appear in the middle of supernova remnants because they should be quite young, whereas pulsars and white dwarfs are quite old objects. They'll be scattered throughout the galaxy. So that's another angle. Multi-wavelength follow-up is also a really good idea. So as one of the radio astronomers who's very famous in our field, Jim Condon, once said, there's nothing so useless as a radio source. And that's because radio is it's indicative that there is some high energy process, but it's very hard to tell what's actually generating that. You can't look at it in a way. So if we could get optical or infrared detections of these sources, then we might have a better idea of like what's actually generating the radio emission, whether that's a neutron star, a white dwarf, or something else. Even maybe a main sequence star, but it's probably really difficult to do that. So that's tricky because both of these sources that we've found so far are inside our galaxy. So it's like instead of like looking through a nice dark area and easily being able to tell where the radio source is and where the star is or the neutron star or whatever, instead you've just got thousands of stars and you know somewhere in an error ellipse is your source, but you don't know which one it is. So another kind of observational angle that I'm going for is to look at quieter parts of our galaxy where there's fewer stars. I know, ironically, we're less likely to find a signal, but if we do find a signal, then we can cross-match it much more easily and get that multi-wavelength counterpart. So those are a few angles, but the key thing about publishing a paper like this is that I'm just one person. I have my strengths and my weaknesses. The community is huge, and I'm excited to see what other people will do with it. I know already radio telescopes in China and in France and the US are all now turning their sights to this object to see what their unique observations can bring. So I'm just excited to see what the community does. It might not be me who solves the mystery.
I have plenty of questions. One of them I wanted to ask you is, how do you feel after having discovered something so weird? Is it frustration, happiness? What is the feeling as a scientist you have, and then as a human being?
I think I've gone through a lot of different feelings on this. I think the first feeling was just frustration, because I assumed I'd done something wrong, right? When you find a signal that you don't understand, you assume somebody's turned their mobile phone on, or I've made a terrible mistake in how I've done some part of the data processing towards this. And certainly with the first source, when we only had detections from the Murchison Wide Field Array and we didn't have any other radio telescopes able to confirm what we'd seen, because we found the source too late after it switched off, it was a little frustrating, because it's like you found this really cool thing, but nobody else can look at it. So you feel like that character in a story that's seen a ghost and nobody believes them. Finding the second one, tremendously exciting, because we could get that follow-up, we could get that confirmation. And the paper author list is comprised of like this wide group of national and international astronomers who have all used different telescopes. And so it's just phenomenally satisfying to create an experiment, design an observing campaign to look for a thing, find that thing, and it actually all to work, sort of validating as a scientist. And I guess finally, it's just incredibly exciting. I always think if I could go back and talk to my 8-year-old self and say, you will find, right? You will grow up to be an astronomer, and then you will find a kind of astrophysical source that defies physics and is inexplicable and sends the world into a frenzy. I'd just be incredibly proud of future me and very excited. So it's really wonderful, I'd say, to have been able to make this discovery, and with a fantastic, supportive team and some wonderful students to work with. It's just been a brilliant journey. So yeah, all the emotions. It's been great.
Okay. We have more people joining us from Michigan, Connecticut, someone from Houston, Texas. I don't know if someone from your family is joining us as well.
No, they don't live there anymore.
So if you have any questions to ask Natasha, please write them down in the chat. We will select a few of them. I have a question here. What's the distance of this object? Is it in a galaxy, outside, close to the center of the Milky Way? Where is it? Where is it located?
Yeah, great question. So one of the fantastic things we can do with radio sources is actually locate how far away they are by the amount that the interstellar medium slows down the pulses. There's this effect called dispersion, where very, very low frequency radio waves are slowed down by interstellar plasma. The lower the frequency, the more the slowdown. So basically, in terms of like how that sort of sounds to a radio astronomer, is it kind of sounds like boom, where all of the high stuff arrives quickly and the low stuff gets slowed down. And so we have what's called a dispersion sweep, and we can measure that really precisely. We can combine that with models of the electron density in our galaxy, and we can work out that this source is about 15,000 light years away. So it's inside our galaxy, but it's quite far into our galaxy. It's not quite next to the galactic center. It's in the Scutum constellation, if that means much to you. Or you can use the 1839 minus 10. Those are actually the coordinates in retiception and declination. But it's inside our galaxy, the Milky Way, and it's quite deep into it. We're seeing this about 3 times further away than the first source we detected. So they're very, very bright to be able to be visible across that huge distance.
Thank you. Thank you for taking the time to explain this. Another questions we have from a user here, from someone watching us, is this kind of sources create gravitational waves toward the Earth?
That's a great question. It probably would. So rotating objects do produce a little bit of gravitational waves, but they're way beyond the detection capabilities of our current instruments. Binary objects, so 2 objects sort of orbiting each other, produce much stronger gravitational waves. And our source could be in a binary. Unfortunately, if it is, we can't tell. What would have to be happening is the binary would have to be essentially face on to us. Mm-hmm. So if the source were moving like this and it were getting closer and further away from us, then the pulses would be changing their arrival time over the course of that 33 years. but it doesn't seem to be doing that, right? It just seems to be locked in place. But if the source were going around like this, the arrival time of the pulses wouldn't be changing, and so we wouldn't be able to tell. 15,000 light years away is also really hard to use optical and infrared telescopes to look for orbits. Like, that's really far. So so far we don't have any indication that it's in an orbit, and that would be the thing that would allow it to produce really detectable gravitational waves. It's also probably too small. Like, our detectors at the moment are capable of finding supermassive black holes or stellar mass black holes quite nearby smashing into each other. This thing's probably like millions of times smaller, or at least thousands of times smaller. So probably beyond the capability of our current instruments.
All right. So I know you already explained this, but Dexter Mayuhe asked again this question. Could you again explain what the pulsar and the Magneta, and if they are really family of neutron stars?
That's right. They're both types of neutron stars. So at least that's the best explanation that we have. Like, nobody's gone out in a spaceship and looked at these things. It's the best theory that fits the data. So neutron stars are this endpoint of stellar evolution. When a massive star explodes, everything collapses down. Some of it goes out in a supernova and the rest of it collapses down. And the gravity is enough to squash all the atoms together, the protons and electrons, and combine them to make neutrons, but not so much that it collapses into a black hole. So there's a very tight mass range, about 1.2 to 1.9 solar masses, like the masses of our sun. In that range, you get a neutron star. And just like a figure skater, when they're doing a spin and they bring their arms in and they spin really quickly, a normal star is spinning, once every 11 days or, once a day or something like that. And as it collapses down, it spins up very quickly. A similar process happens with the magnetic field. So the magnetic field of our sun is big, but it's spread out over a very large object. And when you get a collapse like this, it becomes very strong and dense, for want of a better word. So pulsars and magnetars are neutron stars in which this process, where you've kind of concentrated the magnetic field, has occurred. It's quite a bit more complicated than that, but that's not my field. So that's the simple explanation.
So when those Magneta were discovered, when was the first time we talk about Magneta? Because frankly, I discovered the existence of these bodies talking to you a year ago. So
sure.
I'm a planetary astronomer.
There's only about 30 magnetars known, and it's actually really only in the last 5 years, 10 years, where it's become known as a specific class. The classic thing happens that always happens with astronomy is that the gamma ray astronomers discovered something called soft gamma ray repeaters, and the X-ray astronomers discovered something called anomalous X-ray pulsars. And the radio astronomers discovered these weird pulsars that were switching on and off. They were called 3 different kinds of object for about 15 years, until all those different astronomers from different wavelengths had enough conferences together and went, wait a minute, we can see gamma rays from these X-ray sources. We can see radio waves from these gamma ray sources. What would make sense?
It's
and
the same
figured
body.
out this unifying picture of Magneta. So it's such an intense, distorted magnetic field that disrupts the neutron star crust, produces X-rays, gamma rays, and occasionally radio waves. And that's the kind of unifying picture that knits together the observations.
Yeah, I can totally imagine the conferences where people are talking about the same object without realizing it. And then one day, one student go to a bar to talk to another student, to another postdoc, and they're talking about the location, and they realize that this is the same object.
Same thing, yeah. We're very biased by the wavelength from which we come. We think that's how to see the world. And it's those conversations that really advance our knowledge.
Okay, I'm going to have a final questions for you. So I went to a conference in Koriyama, Japan, last week or 2 weeks ago. You give a review talk, which was very good, by the way. And there was a booth about something called the SKA. Do you expect, could you first tell us what is the SKA? And then if you expect anything coming from this facility for your research, and what?
Absolutely. So the SKA stands for the Square Kilometer Array. And it's actually the reason I moved to Australia. It's going to be partly built here, the world's largest radio telescope. We're going to build the low frequency part here in Australia and the sort of high to mid frequency part in South Africa. So there'll be two different observation sites, but that's okay. You have to build two different telescopes anyway, because you can't really do the low frequency observing with the same design as the high frequency. And yeah, it's just going to be an enormous number of dishes, and in the low frequency case, stations, and both built in very radio quiet sites. So there won't be any radio interference unless Elon Musk keeps putting things in space. Well, we'll figure out a way to deal with that, and I'm sure people are working on that with all of the commercial operators. But yeah, we will then be able to solve a whole bunch of different questions. So there's very sensitive radio observations. We can look back in time at distant galaxies, look at how their gas evolved with time. We can probe for the first stars switching on, the epoch of reionization. Huge amounts of pulsar, fast radio burst research. Of course, there's a big SETI component, cradle of life, scanning for technosignatures across thousands and thousands of stars kind of continuously. And yeah, from my point of view, will absolutely be a brilliant machine for finding more of these long period transients. But the point I'd like to make is that the MWA, the telescope with which we discovered these long period transients, was also had its whole range of science goals, which we've been all working toward. But we opened a new space into the universe with that telescope. And that allowed us to discover the long period radio transients, which were not a predicted thing. Nobody expected to find these things. And so that's why we don't know what they are. We've got no really good theories. So I think the SKA will do the same thing. We'll be able to open a new window onto the universe. We'll look at it in a different way. And I'm most excited about the things that we don't even know are waiting for us to find. That's going to be the cool stuff. And I hope I'm in my midlife, mid-career. I've still got a few years on me. I hope to be using that telescope to discover the unexpected. That will be the most exciting thing.
That's an excellent way to end this conversation, to discover the unexpected. Thank you. Thank you very much, Natasha, for taking the time to talk to us today about your research. And I hope to see you soon to talk about the next discovery, because now you become a regular to our SETI talk and SETI Live.
Working on it. Thanks so much, Frank, for having me. And thanks everyone for listening.
Thank you, everybody. That was the SETI Live by the SETI Institute. Thank you for watching. We are a non-profit organization. As you know, you can support us by sharing this video, talking about us to your friends and your family, and say, hey, this is cool. Look, they found some way weird stuff in the sky, and we still don't know where they are. So maybe one of you will be inspired and help Natasha in the future to identify the true nature of this body. And also, don't forget that you can also help us by joining our newsletter called Journey. You can also join our social media. We are almost every platform now. And finally, if you feel inclined and you want to support research outreach at the SETI Institute, you can make a donation. Just simply go to SETI.org and click on donate or something on the top right. And you can make a small donation that will be used to study more weird and unexpected body in the sky. And in the meantime, enjoy your evening, your morning, or your day, and see you soon for another SETI Live. Bye-bye, Natasha. Bye, everybody.